Hello everyone, and thank you for joining us for this webinar. The webinar today will cover volt-var optimization or VVO. VVO is the process of optimally managing voltage levels and reactive power to achieve efficient grid operation by reducing system losses, peak demand, or energy consumption in any combination. ETAP volt-var optimization allows engineers, operators, and planners to design, automate, and continuously optimize power systems within operating parameters, especially when running at system capacity limits. The goal is to improve overall efficiency, reliability, and cost effectiveness of electrical system operations, planning, and maintenance. In this webinar, we will discuss the industry challenges and benefits of a model-based VVO for long-term planning and operational control. We will also gain insights how customers can practically achieve proactive reduction in energy waste, CO2 emissions, reduction in energy consumption, as well as extended equipment lifetime. So let's go ahead and get started. Before diving into the integrated volt-var optimization topic, it is important to revisit the concept of VQ triangle. Reactive power in VARs is created by energizing transformers and powering motors, pumps, air conditioners, and other similar devices. These electrical appliances, of course, have large coils and magnets inside them and require both real and reactive currents to operate. Real current, of course, does the actual work, and the reactive current enables the production of magnetic fields inside the inductors. Both real and reactive currents flow through transformers and feeders. In contrast, of course, electrical loads such as incandescent bulbs are purely resistive and only require real current to operate. Real and reactive power combined is known as apparent power, which is measured in volt amps or VA. Although utility companies must supply both real and reactive power, they typically charge consumers for real power. To cover the cost of unbillable reactive power, power factor penalties are charged by generation companies to the utility distribution companies and, of course, from the distribution companies to certain consumers. Power factor penalties are proportional to the amount of reactive power supplied, and it refers to the ratio of real power divided by the apparent power. So taking your favorite beverage, such as your coffee, it's nothing but the ratio of the coffee divided by the latte. And that essentially gives us the effectiveness of the power being supplied. For example, a power factor of 0.95 tells us that 95% of the supplied power is real power and the rest is reactive. We can augment our power triangle by essentially also introducing another term, which is harmonic reactive power, or QH. And that essentially corresponds to another term, which is distortion reactive power, to complete our overall power triangle. Based on our example, we can see that the power factor correction has certain benefits. In other words, getting more coffee than the foam or the latte. The benefits of power factor correction include saving energy, where the loss can be reduced up to 30% depending upon the level of optimization that's being applied. You can also increase energy efficiency by optimizing the power factor, and your power quality increases, therefore increasing performance, reducing unplanned outages, and lessening the potential damage to the electrical equipment. You can also reduce equipment cost through an efficient power factor that allows you to use smaller transformers, switch gears, and cables, which improves the overall reliability and lifespan of the equipment. And finally, you can also reduce CO2 emissions by eliminating energy waste and overall consumption, which reduces heat, transmission losses on equipment and systems, and in return reduces your CO2 or carbon footprint. So let's take a look at the volt-var or VQ problem, where we essentially have our substation voltages expressed in terms of the service voltage. And in North America, we typically use 120 volts as our nominal voltage. Therefore, 120 is set as a nominal at the service end of the feeder, with 114 and 126 volts being the minimum and maximum values for this particular example. And then we can observe the voltages at certain locations along the feeder as you move further away from the substation, and we'll observe the voltages on location A and location B. So under normal conditions, the voltage level is highest at the substation and lowest at the end of the circuit. The voltage might droop below the minimum acceptable level for some customers, especially during heavily loaded conditions. So you can essentially see a region of low voltage appear for a given set of heavy loading condition. So several solutions can be used to optimize the voltage profile across the circuit. One of them is to simply raise the manual tap setting on the substation transformer to correct the peak load problem. The substation load tap changer and line regulators can correct voltage without correcting the loss. So by simply adjusting the tap, we can essentially avoid the low voltage condition. But in this situation, when the feeder loading is light, high voltage could be a problem at the substation end of the feeder. So therefore, this is not an optimal control solution, and it is typically replaced with a more volt-var control and optimization approach. So as we can see, for the case of voltage rise or voltage drop, we can use volt-var control as a strategy to essentially alleviate that kind of problem amongst other strategies that are available to us. We can also use volt-var control as a strategy for providing a means to provide source of reactive power. So can you really benefit from volt-var control? Any small to large power distribution system can benefit from volt-var control. If you have your own substation or you are the only customer on the utility feeder, you are definitely a good candidate for volt-var control. If you have voltage regulation capability, which will minimize the initial cost of a volt-var control or optimization system, or if you have an existing infrastructure such as metering or SCADA, you can again definitely benefit from a volt-var optimization or control strategy. You do not have to be necessarily a utility power distribution system to take advantage of volt-var optimization or volt-var control. So how do you quantify the benefits? So for volt-var optimization and control, you can essentially expect increased real power and reduced VARs, which is the main objective and purpose of providing this type of optimization and control. For a 1% voltage reduction, you can expect about a 0.8 real power reduction. So therefore, for a system voltage reduction of about 3%, you can expect the feeder energy to be reduced by about 2.4 to 2.5%. And these are just baseline numbers that can essentially get you started in terms of providing a conceptual feasibility for the project. But of course, detailed analysis per system, per feeder, can give you more exact numbers. And we'll take a look at that through a few examples. Traditional VQ control or voltage reactive control allows us to maintain acceptable voltages at all points along the distribution feeder under all loading conditions. It allows us to operate the distribution system as efficiently as possible without violating any load and voltage constraints. And it can support the reactive power needs of the bulk power system during emergencies. Traditional devices for VQ control include voltage regulators or transformers with load tap changers or LTCs that automatically raise or lower the voltage in response to changes in load. It also includes capacitor banks that can supply some of the reactive power that would otherwise be drawn from the supply substations. And it can also include static VAR compensators or distribution STATCOMs or static compensators throughout the electrical distribution chain. Some of the volt-var optimization and control technologies can be classified as centralized, decentralized, and edge network. So let's take a look at the first one, which is traditional VQ control using standalone or edge control. This involves using a current or voltage sensor that sends the measurements to a standalone controller, which then can send a control command signal to a capacitor bank or react the same way and control a voltage regulator either in single direction or bidirectional control mode. Some of the weaknesses of this type of controller include the lack of flexibility to respond to changing conditions out on the feeder. For example, if there's a feeder reconfiguration, there's presence or absence of DERs, and when these changes occur, the controllers may not operate in an optimal fashion. This approach also does not provide any voltage feedback for critical measurement points on the feeder, which is necessary for closed loop control. As a result, the system would continue to operate with a greater margin above the minimum acceptable voltage so that you can avoid violating the minimum voltage constraints. System operators are also not able to monitor the operation of the switch capacitor banks due to lack of communication facilities. And if the controller, switch, or the bank itself fails, the utility may not know this until a manual inspection occurs, which is very commonly the case. There's also minimal coordination between the standalone controllers. So typically the controllers include coordinating time intervals to ensure that the controllers do not execute conflicting actions. That means they're not hunting the set point with other standalone voltage and VAR control devices. Due to some of these limitations, the standalone controller method may not work well in circumstances where feeders are frequently reconfigured and on feeders that include large-scale distributed generation. However, the controllers themselves play a significant role as endpoint device controllers and invaluable, especially to provide a fail-safe mode for the system. The decentralized approach is the most common approach to VVO in use today, and it's basically based on a SCADA rule-based approach. This approach determines what volt-VAR control actions are to be taken by applying a predetermined set of logical rules to a set of real-time measurements from the associated feeder or substation. For example, if the voltage measured at point A is less than 120 volts and the reactive power measured at the substation end of the feeder is greater than 1000 kVARs, then switch capacitor bank to on position. These rules are determined in advance by distribution engineers and operators using power flow analysis. The rule-based approach requires a SCADA facility that provides communication coverage to any point on the distribution feeder. This is not a problem for electric utilities that have distribution SCADA facilities. However, adding this facility can be expensive for utilities that do not already have a distribution SCADA. The rule-based approach does not work well on distribution feeders that are heavily meshed because the rules become too complex if a large number of switching possibilities exist. Because again, a power flow analysis is used to determine the rules. It is often not possible to anticipate, therefore, all the possible operating conditions of DERs in a fixed set of rules. Therefore, the rules-based approach may not be effective on feeders that, again, have a high penetration of DERs in the network. Another drawback to this approach is that as the system changes significantly or is operated in abnormal configurations for long periods, the logic on which the substation ID will be making decisions will be based on a stale network model configuration. In some instances, control center operators might turn off the centralized VVC at the substation because many power quality issues may be generated when this VVC method is working within an old or stale network model. So the traditional VQ control using the standalone or decentralized approach has a couple of disadvantages. The voltage and VAR control devices are basically regulated in accordance with locally available measurements, such as voltage or current. On a feeder with multiple voltage regulation and VAR compensation devices, each device would therefore be controlled independently without regard for the resulting consequences of actions taken by other control devices. This practice often results in sensible control actions taken at the local level, but they tend to have suboptimal effects at the broader or system level. So ideally, information should be shared amongst all the volt and VAR control devices. The control strategy should be comprehensively evaluated so that the consequences of possible actions are consistent with optimized control objectives. This could be done centrally using a substation automation system or a distribution management system, and therefore this approach is commonly referred to as integrated VVO, which we'll talk about in a little bit more detail. But before we get to the integrated VVO, let's just talk really quick about high penetration of DVRs, which is essentially an industry trend where PVs and wind turbines have intermittency and the dependency on voltage and reactive power. And this dependency on voltage and reactive power to produce real power has an effect on the balance of the system. Variability on the solar irradiance, the variability of the PV module temperature, the module power dissipation, shading or soiling, cabling, switchboard and circuit losses, as well as inverter and transformer efficiency have an overall effect on the real power output of the PV or wind turbine that are distributed throughout the feeder, and therefore they have a different demand or intermittent demand on the voltage and reactive power controlling capability as well. So therefore the VVO algorithm should be able to take into account the variability of DERs such as solar and wind when it's factoring in the optimal set points for the capacitor banks, voltage regulators, and so on. So of course we will see our distribution grid switch over from a passive to a more active distribution grid with more distributed energy resources and inverters being available on the utility distribution circuit. And the effect of a large PV system or large groups of distributed PV systems is such that as the real power is being injected into the feeder, it tends to unload the feeder by providing that required real power at the local level, causing the voltage on the receiving end of the feeder to not drop but essentially climb. So the intermittency of the PV at the end of the feeder has a reverse effect on the voltage profile at the end of the feeder, and therefore must be accounted for on a continuous basis, which again cannot be done through just standalone controls or simple rule-based approaches. In the fall of 2017, for example, California became the first US state to require the use of advanced or smart inverters to essentially take care of this problem. These changes were implemented through updates to Rule 21 and then require inverters to have certain capabilities to ensure proper operation of the electric grid as more and more renewables are connected. Phase 1 went into effect on September 2017 and requires that any solar project which applies for interconnection to the grid must use an advanced inverter capable of performing 7 autonomous grid support functions. For example, during and after a disruption of the grid, variations in voltage and frequency may occur. Historically, PV systems have been required to immediately disconnect when these conditions were detected. However, if a large amount of DER capacity disconnects at once, this could further destabilize the grid. Similarly, the grid could be stressed if many solar installations reconnect to the grid at once after an outage or increase their power output to a steep rate. So therefore, smart inverter functions were introduced to allow systems to remain connected to the grid under a wider range of voltage and frequency levels. So therefore, we can see that our traditional system, where the voltage is high at the substation end and low at the receiving end, was normalized and optimized through the use of smart inverters. And the smart inverters therefore also use a VQ curve to provide voltage and reactive power support at the local level. We can see that V2 and V3 represent the deadband of the smart inverter, whereas V1 and V4 represent the higher and lower voltage ranges of the smart inverter. At the lower end of the voltage, the smart inverter is producing more reactive power to boost the voltage up, and at higher voltages, the smart inverter is inductive and absorbing reactive power to essentially bring the localized voltages down to nominal values. This type of smart inverter control is also known as autonomous control, and it, however, has certain limitations, such as the stability considerations and the voltage sensitivity changes by using a subset of the DERs that are providing only, again, localized control to a particular feeder or a certain part of the feeder. By providing a subset of control, again, it is not an optimal volt-var optimization because it may not be utilizing all the available resources for providing optimal dispatch. Therefore, involvement of the ADMS is needed to mitigate violations of any operational limits such as feeder loading and to optimize the overall operating condition under different operating topologies. Therefore, there's a need to extend beyond traditional VQ control in terms of modeling the load and voltage sensitivity such as constant Z, constant current, constant power. Consider the voltage and thermal limits that are traditionally not considered by standalone or SCADA-based devices where the full digital twin model is utilized for the volt-var optimization and control. That model should include subtransmission as well as the secondaries to understand the full impact of the source and load in the system when the optimization is done. Include DER intermittency, but also include their dispatch at the same time so they become part of the coordinated control. Use the present as operated network model, which basically implies that you're not only just using the existing operating topology, but also using the outaged state of the network while maintenance or any other activities are ongoing, such as temporary jumpers, cuts, and so on. Maintain power quality and voltage stability throughout to ensure that the sources and loads are not disconnected and reconnected in bulk. Share infrastructure with the ADMS to reduce ownership cost, and therefore this essentially drives the need for an integrated model-driven volt-VAR optimization and control. Therefore, ETAP ADMS is based on a centralized volt-VAR optimization and control objective that is used by operational planning, network planning, as well as engineering of power distribution systems. The integrated model-driven volt-VAR optimization and control provides many benefits, such as the ability to dynamically adjust and reduce losses and minimize demand. The industry experience with such systems has shown that you can achieve 1.5 to 3% demand reduction using an integrated model-driven VVOC. The customer engagement is therefore not required to achieve these efficiencies, and you can achieve maximum benefit in case of constant Z or constant impedance loads. The implementation of a model-driven VVOC is a reasonable cost to implement and maintain. Implementing VVO is cost effective because at application of VVO at only 15 to 25% of the substations gives you a return on investment that is easy to justify an overall DMS investment. So the integrated model-driven VVOC has objectives that are expanded beyond the traditional volt-VAR control. It includes the basic requirements to maintain acceptable voltages, support major smart grid objectives, but also includes accomplishing energy conservation, improving efficiency, reducing technical losses, promoting a self-healing grid where VVC or VVOC plays a role in maintaining a voltage after self-healing has occurred, especially when you have disconnection of resources and reconnection in the system. The balancing of voltage and VARs has to be maintained under those circumstances. So the integrated volt-VAR optimization and control follows a very simple process. It requires monitoring the field devices, running distribution state estimation as an optional capability, running volt-VAR optimization algorithms, followed by controlling commands through the electrical SCADA, validating that the commands have been executed, and continuing to monitor the field devices for any subsequent changes. The problem of optimizing a distribution system involves multiple objectives such as minimizing the losses and reducing the overall power demand. Therefore, in ETAP, the systems are modeled as multi-objective optimization problems. Therefore, you can have more than one objective function. The objective function can include CVR or conservative voltage reduction, peak shaving, minimization of power loss or efficient power flow, as well as optimization of voltage profile. CVR allows us to maintain the minimum regulatory voltage limit in the system. The voltage is defined as a target, and ETAP ensures that the minimum voltage limit in the system is maintained and honored. Peak shaving involves reduction of system capacity. So as the system capacity needs reduce, the power generation need reduces at the same time. Minimization of power loss or efficient VAR flow implies minimization of the reactive power flow from upstream sources by using localized switch capacitors and other VAR control devices, therefore reducing the reactive power losses throughout the feeder. Optimization of voltage profile allows a more flatter voltage profile should it be chosen to be done so. In our discussions, we'll focus a little bit more on CVR or conservative voltage reduction. Here's a simple table that shows us at the service voltage, if the nominal voltage is changed from 122 volts and dropped down to 118 volts, implies for different appliances a conservation of power provided as a percentage. So therefore we can see the fans have about a 6% reduction in power consumption, followed by CRT TVs, compact fluorescent lights, as well as incandescent bulbs. So this is where we can see that the constant impedance type loads have a significant conservation of power as compared to the constant current or constant power loads. By looking at a daily demand curve and applying a CVR capability where the endpoint voltage is purposefully reduced to a point just above the ANSI voltage limits allows us to conserve power based on the load type in the circuit. And the area in gray essentially represents the energy savings that are delivered and the CVR power demand curve as implemented over a function of time. So let's take a look at the design and network planning aspect of volt-var optimization and see CVR in action. So we're going to go ahead and set our objective, select the control variables, run volt-var optimization, and view our results and settings and savings accordingly. So let's take a quick example of volt-var optimization in action in terms of network planning. So in ETAP, we can see our geospatial view as well as our single line diagram view that gives us a view of all the substations and the composite networks that are in the system. We can use the ability to synchronize our presentations, so you can easily click on a particular location and the program will show you the corresponding geospatial location, or you can essentially zoom into a particular location on the GIS, for example this node right here, and the program will tell you exactly where that switch or node is connected in the system. With that understanding, we can actually switch over to our volt-var optimization with this integrated view and take a look at our study case for some of these objectives and options. So we can see that we have the ability to update load tap changers, capacitors, and voltage regulators. We can also do a continuous calculation based on a predefined cycle. And our objectives include things like conservative voltage reduction or peak shaving, minimization of losses or efficient power flow, and optimization of voltage profile. We can either optimize our entire system or we can optimize a feeder at a time. And when we say we can optimize the entire system, that includes the transmission, subtransmission, secondary, as well as load distribution levels. You can also include the load tap changers that can be automatically controlled or the ones that are on manual control that can be neglected or ignored. The switch capacitor banks can again be automatically or manually controlled in the system. And you can also include inverters or PV arrays as part of the dispatch. So these are the passive or even the active or smart inverters that can be included as part of the calculation. And our loading can essentially include multiple sets of loading to do the what-if analysis, as well as alerting for voltage as well as thermal limits for various types of components. So with that, we can go ahead and actually run our volt-var optimization calculation and see the results in terms of a viewer, as well as see the results on the diagram directly. So we can see the power flow on our single line diagram, and we can also see the results of volt-var optimization directly on our GIS as well, including the substation values, the feeder values, and so on and so forth, which are shown per phase. So if you take a look at our viewer, which is giving us the summarized information for our system, we can see that our losses have gone from an initial value of 34.5 to 28.9. So there's a 5 kilowatt reduction of losses in the feeder, but that's really not the main purpose of volt-var optimization, because as we are reducing the voltage in the system, we are reducing demand, and therefore we are also reducing the actual losses. So therefore the improvement may not be significant, but the CVR itself gives us the story where the lowest possible voltage on the node is 99.25%, and that the program has managed to bring it down to 95.01. So again, this is the lowest voltage found on that entire feeder, which has been reduced by about 4.25% to reach that minimum value. So this requires again a system level coordinated control to hit that objective and not have any node that violates that minimum voltage amount. And this value of 95% is user adjustable, so you can essentially set it to your CVR target level with certain conservatism built into it. Based on that, we can see that this 1 megawatt feeder has a demand reduction or peak shaving of about 100 kilowatts. So we're going from about 1.2 to about 1 megawatt. And we are able to do this by adjusting the tap changers on our transformers, switch capacitors, as well as our DER inverters in the system. So therefore, the model-based approach takes a geospatial model as well as a single line diagram model of this electrical system and utilizes our standard ETAP capabilities to run a base power flow as well as a volt-var optimization and provide a initial and final comparison that you can visualize and analyze under different operating conditions and different loading conditions at the same time. So therefore, with the ETAP integrated VVOC solution, if we look at our problem again without integrated VVOC for normal load, we can actually adjust that such that the sending side voltage and the receiving side voltage under normal load is within reasonable limits. And without VVOC, we would normally see a lower voltage condition, but with VVOC, we can again bring in the voltages to within acceptable limits. And of course, for our final case where you have a lightly loaded system without integrated VVOC, you can apply ETAP VVOC and you may see a slightly lower value at the substation sending side, but a higher value at the endpoints, depending upon, again, where the compensation devices are actually located in the system. Which brings us to an important factor, which is known as a CVR factor. How do I know that my conservative voltage reduction is performing optimally? So the CVR factor is essentially a percentage of the change in energy consumption divided by the percentage change in voltage. So for our example that we just looked at for feeder 1, the CVR factor is basically 10.6% change in energy consumption divided by 4.25% change in voltage, which is a CVR factor of 2.5. So in other words, what you can say is that for every 1% change in voltage that is reduced, we are able to save about 2.5% in energy reduction. If you recall from the previous slides, I had mentioned that conservatively you can assume a 3% system voltage reduction can give you at least a 2.5% energy reduction. In our example, we can see that that is essentially translating into 1% system voltage reduction, giving us about 2.5% energy reduction, which is quite good in terms of a CVR factor. So this is essentially a good measure of how effective the volt-var optimization and control is behaving in the system in design mode, which can then be applied and tested in operations at the same time. So when we move on to operations using ETAP ADMS, we take the same distribution model and the ETAP volt-var optimization studies that we have already done and apply the ADMS server, distribution state estimation, and unbalanced power flow as applicable, along with our geographic display, outage management system, and the SCADA. So this formulates the entire bulk of ETAP ADMS amongst other capabilities, which connects to meter data management systems for load data consumption, the ability to view and send manual switching orders to the field crews through the OMS, look at the temporary changes such as the operational switching through the SCADA side, and also track the maintenance changes through the enterprise asset management linkages. So the ETAP ADMS essentially takes advantage of the standard connectors and capabilities to visualize and utilize the data. But in addition to that, it also takes into account the ability to control things such as substation load tap changers, voltage regulators, and using AMI head-ends particularly, we can also communicate to capacitor banks, smart inverters, and energy storage systems that are not necessarily the large-scale systems, but the residential and small commercial size systems, in addition to the ones that might be connected directly to the utility feeder. So of course, every topology for every customer may look a bit different, but this is a very standard approach for an integrated volt-var control using ETAP. With the distribution model, the SCADA connectivity, as well as the AMI and MDM connections, we can then take the topology of the system, run distribution state estimation, use the estimated or AMI loading, run volt-var optimization, and even run a capacitor relocation to essentially provide more optimization of the existing assets in the system and of course view our results and settings as the end result. So in this example, we'll go ahead and take our existing model online and essentially see what happens when we connect this to a distribution state estimation as well as our volt-var optimization engine. So if we go ahead and essentially run a load allocation or distribution state estimation, we can take the meter measurements that are available to us and allocate all the power to all the three-phase as well as single-phase loads inside the circuit. And we can then go ahead and bring up our load allocation study case to see that it is set up correctly, switch over to volt-var optimization and control, and essentially set VVO to run on a predefined interval with a CVR objective for certain feeders such as feeder 1, feeder 2, set up our load tap changers, switch capacitor banks, and then go ahead and run volt-var optimization in a continuous mode. So when we're running it in a continuous mode, we can see the results that are being provided to us, such as the CVR results, the peak shaving results, and so on, as function of time. And you can define the speed or the schedule at which the VVO runs, which can be on a preset interval, or it could be on demand, or it could be event driven, or any other combination that you may choose to, such that you can get continuous volt-var optimization on the feeder circuits. There are many different approaches for doing so. You can run volt-var optimization for the whole day and then not run it the following day. So you can observe the differences between having a volt-var or not having volt-var in the system. Or you can do it on a periodic basis, which is good in terms of comparison. There are many utilities who may even do this on a weekly basis or on a 3 or 4 day basis, where they may run the system with VVO and without VVO and observe the cost savings and the demand savings in that respect. There's also a online web viewer that we provide with the ETAP VVO that gives the user the capability to view advisory as well as supervisory information. You can also look at loss and voltage summaries, trending information that's telling you how you're performing in terms of CVR effectiveness. So let's go ahead and take a look at our web interface in more action. In our web interface, we can see the current operation of the system per feeder, where we can observe the summary before volt-var optimization as well as after volt-var optimization in the system. And as part of this, we can also see the total energy reduction before and after on a periodic basis, such as daily, weekly, monthly, yearly, as well as the position of the tap changers, the capacitor banks, and the inverters in the system on a regular basis. You can also look at the VVO recommendation as they're coming through per event or per scheduled time interval. And for every single event, you can also drill down and see the details of exactly which components were dispatched or adjusted as function of time. And these adjustments are essentially dispatched either automatically or provided to the operator as a recommendation. So that's essentially what we call advisory versus supervisory. You can also look at the losses, voltage summaries per feeder, along with the number of control signals that have been sent, as well as the monitoring of the control signals, whether they have been executed or failed to execute. Followed by the trending information, which can again be seen per feeder. That includes the active reactive power, voltage thresholds, power factors, controls, as well as the before and after, or essentially the base case, as well as the recommended VVO case, to see whether the volt-var optimization is being effective in the system or not. So therefore, as a quick summary, the ETAP ADMS using volt-var optimization gives us real-time performance reports, measurement, energy reports, as well as the ability to customize the reports. It gives us a simplified enterprise solution with web-based thin client interfaces, a connectivity model management going from design planning all the way into operations. The ADMS essentially provides high availability or redundancy capability and includes VVOC with smart inverter considerations. The biggest advantage is it's integrated with ETAP planning, design, and analysis tools, so you can essentially design, plan your volt-var optimization strategies and actually implement them using the same digital twin model. And you can also track the asset health and get notifications about the operations counter, the operations monitoring, as well as the timing to perform maintenance on certain assets such as load tap changers, capacitor banks, and so on and so forth. So once again, thank you for attending this webinar on volt-var optimization, and we hope to see you soon in our next upcoming webinar. Thank you.